So hello and welcome back. Welcome to lecture 4-1A on probabilistic sensor models. Our learning objectives for the 4 videos in this series are describing probabilistic sensor measurement models, describe various types of sensors used on a mobile robot, discuss using ray casting to determine the probability of a given shape for a map given a robot pose, as well as a scan-based algorithm for doing that, to devise a maximum likelihood for noise parameters for a measurement model in a mixture model, to discuss likelihood fields to measure models for rangefinders, and to describe map matching, beam-based, and feature-based measurement models. As usual, the content for this course comes from a textbook in a course called Probabilistic Robotics, which can be found at probabilisticrobotics.org. And the authors of that text are Sebastian Thrun, Wolfram Burgard, and Dieter Fox. I hope you will come along with me, and I hope you enjoy. So first, let's recall that Bayes' filters and models were about finding the belief in a robot state, and it was made of 2 parts. One of the parts was the motion model, which was covered in last week's lecture, and the other part is the perception model, or the sensor model, which will be covered in this week's lecture. So probabilistic robotics, remember, it deals with the uncertainty in robotics. We talked about the uncertainty in motion in a robot, and now we're going to talk about the uncertainty as we describe that in the context of sensor measurements. So we want to have a way to model this uncertainty in order to have a belief about the robot's state in the world. Once we can model it, we can determine that state. So it's okay. We know the error is going to be there. We just have to have a reliable model for it in order for us to make decisions about what the robot has to do next. So as soon as we have the sensor data, whether it's random or we can recognize the error, as long as we can find a way to use that to estimate the current state of the robot with that error, then we have done what we need to do in order to solve our robotics problem. The more we can model that uncertainty, the more we can estimate our robot's state. So for environment measurement modeling, you want to describe a process for using the sensor data, the sensor measurements you can find around the world, whether it's measuring a landmark or measuring a person, but we want to be able to use that information to determine what happens next with our robot. So first of all, there are different types of models for different types of sensors. And we all know that a robot's intelligence is tied to the number and the diversity and variety of its sensors. And obviously different types of sensors would have a different type of model. So for example, image sensors are modeled by projective geometry. A lot of times a sensor will give you a pixel data, but if you have for example, a stereo camera, you can use triangulation in order to determine the distance to an object that you find in 2 different images. You can also use sonar sensors, which are modeled by sound waves and a reflection of that back to some surface. So it uses time of flight with a ping and listening for the echo to determine how far to an object. However, the inability of a sensor to reliably measure range is sometimes caused by sensor noise, or with a sonar, it could be crosstalk, or it could also be caused by specular reflection. If the ping from the sonar that goes out can bounce before it comes back, you can get false positive or false negative, or things too close or too far than where they actually are in the world. So probabilistic robotics accommodates for these inaccuracies in sensors by modeling it as a stochastic process, such as a condition probability, as opposed to a deterministic process. So therefore, we use the probability of a sensor Z given a robot's pose in the world, as opposed to knowing exactly where the sensor data is given the robot's pose in the world. So we have several ways of describing maps. So a map is an environment with a list of the objects or landmarks in the world that are relevant to the robot's state and what it needs to know. A map can either be feature-based or location-based. If you have a location-based map, as shown here, they're also sometimes called occupancy grids, and it's volumetric because they contain all of the information about the world, including the locations of free space. So you can have a map M that describes the locations 0, 1 through 9 here, that explains or lists the spaces that are occupied versus the ones that are not. You could also have a feature-based map as shown here, where you now only give information about landmarks and their locations in the world. For example, we have a map here where the most interesting things it tells me are that the robot needs to know that there's a house, a cat, a dog, a ball, and a car. And so it specifies the shape of the environment in terms of the specific locations of these landmarks or these features about the world. So the various types of sensors that you can find on a mobile robot. One of them is a contact sensor, a bump sensor, or a touch sensor, which essentially will give you zero distance or nothing. It's a binary value or like a digital input. You could also have proprioceptive sensors, which measure the internal state of the robot. We've talked about before that an encoder is an example of a proprioceptive sensor that measures how far the wheels have turned or moved, or you could measure velocity or acceleration. So we have an accelerometer, which is a spring-mounted mass, which obviously measures the robot's acceleration. We have a gyroscope, which uses a spinning mass, and a laser light to determine the robot's orientation in the world, roll, our yaw, pitch, or roll. And we could also have a compass or inclinometer, which now uses the Earth's magnetic field or gravity. So all of these give us some information about the robot's pose or orientation in some reference frame. You could also have proximity sensors. So proximity sensors essentially tell you how close the robot is to something, such as an object or obstacle in the world, and can be used for object detection. For example, we know sonar, which we've already talked about, uses time of flight with sound with an echo and ping. We have radar, which uses phase and frequency. We have infrared, which uses invisible light and time of flight to determine the distance to an object. And we also have laser rangefinders, which use triangulation, time of flight, phase, and light to determine the distance to objects around it. You see lasers a lot in mapping for mobile robotics. And you can have visual sensors such as cameras, which give you that pixel data back, which is going to be a little bit more complicated because you're going to have to use computer vision or some kind of image processing to get useful information from it. And then, of course, you also have satellite-based sensors like a global positioning system, which are great, but obviously you wouldn't be able to use for indoor robotics. So a little bit more about proximity sensors. So here we have an example of a robot with a sonar array, and it includes 24 sonar at a 360-degree mount around our robot. And what you notice here is we do have some error. We're assuming the black represents walls in our world and the white represents free space. You see that you are going to sometimes get error. The errors occur when the sonar sends back a value that shows that there's no wall present, such as here when we know there actually is a wall here. And also we get error from sonar that stops short, where they send back the presence of an obstacle where there isn't one in the world. That could be a person walking by, or it could be nothing at all. Here we have an example of a laser rangefinder that has two rotating laser, one in the front of the robot and one in the back. And notice that it seems to have a little bit more accuracy, and it also has a little bit more density in the number of measurements that are returned back to the laser. But once again, you could still have some errors in the environment using even laser. And then here is where you take that laser data and you match it to your map, and you try to use those in order to determine the ground truth of where the robot's data from the robot's laser data is most accurate. So your central task today is to determine the probability of a given measurement knowing the robot's pose in the world. So where do the probabilities come from is the question we need to answer. And we need to explain this by looking at measurements. So typically you're going to have a way to model your sensor data in order to come up with this probability. So let's first look at a beam-based sensor model. So let's say you have a scan Z that consists of K measurements. You want to look at each beam individually. So this would be like the 24 beams on the sonar or the N number of beams on the laser. And you're going to assume that each individual measurement is independent given the robot's position. So that means that the beam at N-1 does not depend on the beam at N, etc. So using this independence assumption between the noise and each individual measurement really simplifies this problem. And this is similar to how we use the Markov independence assumption to talk about independent noise over time when we talked about motion modeling. So the way we solve this problem is we multiply all of the probabilities for each beam together, given one sensor reading and knowing the map of the environment. So if we have the sensor data Z, where Z1, Z2 to ZK represents each one of them, the probability of Z given the robot's pose in the map would be the product from K equals 1 to K of the probability of Z sub K given XM and so on. So measurement errors for range measurements. Notice here, we have a robot that is traveling through a corridor, and once again, we identified several different types of error. The first one is that the beams are reflected by the obstacles. So obviously, that's when the sonar or laser is working reliably and it's sending back exactly the distance and presence of a wall or door in the corridor. But then what about when beams reflect by a person or crosstalk if we're talking about sonar? So then you're going to get a beam that stops short. And so those may model presence of things in the world that will not be shown on the map of the environment. Then you'll also just get some random measurements that may show things that aren't a person or thing in the world, and it's just really just a sensor error. And then you will also get some maximum readings, and these may be caused by specular reflection or diffuse reflection, as we talked about before, where the incident angle actually sends the signal out somewhere before it comes back. And examples of those are when the beam actually goes through a wall. So our basic measurement algorithm is range may be measured along a beam, such as with a laser rangefinder, or it may be measured along a cone, such as a sonar or ultrasonic distance sensor. And we're going to use this model, no matter what kind of sensor we have, where we think of each sensor measurement as an individual or independent, given the robot's pose at that time and the map at that time, as a mixture of the 4 types of error that we just discussed here. So we're going to correct our range with our local measurement noise, and we're going to also correct it due to unexpected objects or just failures where it actually does not detect anything at all, or for these random measurements. So this proximity measurement can be modeled caused by things like a known obstacle, crosstalk, unexpected obstacles in the world, as well as missing obstacles together. Another example of missing would be going through, for example, glass. And so this noise due to this uncertainty can be caused by these 4 things, like measuring distance to a known obstacle, in position of a known obstacle, in position of additional obstacles, and whether the obstacle was missed or not. And this concludes our initial lecture on probability sensor modeling. I hope you come back. Have a great day.